All right, hello, this is Miss Weaver, and this is part one of the video for section 9.1. In this section, we're going to talk about two of the main concepts in section 9.1, and that is understanding inference and also calculating a point estimate for a population proportion. And so, what is statistical inference? Well, if you're familiar with synonyms for infer, the word infer, one of them, if I want to infer something, is basically to assume something. I'm using information that I have to make an assumption. And we did this back in the first part of the semester when we were still in class. And I looked around the room and I saw a few people wearing Tennessee shirts, and I said, I'm going to infer that you are a Tennessee fan. And some other people had different things on, and I made some inferences. And a few times I was right, and then once or twice I was not. And that's the way assumptions go. Even with information, sometimes we can still make an incorrect assumption. So we do have to be careful about that, but basically statistical inference is just assuming something about a population there we go. Based on a sample. So we've been dealing a lot with sample statistics so far. We've been able to find mean, median, mode, standard deviation, range, interquartile range, quartiles, all these wonderful things that we dealt with in chapter 3. And we're going to now use those things not just to describe a sample. We're not just doing descriptive statistics anymore. We're now going to use that information to infer something about the population. That's inferential statistics. So we're taking it a step further. We're now going to use that sample to say something bigger about the population. All right, so we're going to go back to chapter 1, where we talked about parameters versus statistics. And if you remember, our parameters dealt with a population. And our statistics dealt with or came from a sample. And we had different symbols for each of these. So for our population mean, if you remember from chapter 3, we wrote all these out, but our population mean was mu. Remember, it's an M that looks like a U. It's a Greek letter. And so mu was our population mean, and our sample mean was X bar. We also had a population and a sample standard deviation. So our population standard deviation, and I'm going to abbreviate, was sigma. And our sample standard deviation was simply an S. Now, you may or may not remember us talking about the population versus the sample proportion. We didn't use it a whole lot, but I just wanted to make sure that we understood that it existed. And so we did write it down somewhere at some point earlier. But our population proportion it would be great to continue to get to use a Greek letter because we've used mu and sigma for our parameters, and they've always been a parameter for the Greek, or a Greek letter for the parameter, and one of our regular English alphabet letters for the statistic. Well, we can't do that because the Greek letter P is pi, and pi is taken. So pi is off limits. We won't be using that in this class. Instead, we'll just use a letter p. But we will dress up p a little bit for the sample proportion. You may or may not remember, we call that p hat. And so p hat, sample proportion, that's just like finding the probability or just the proportion of a sample that hold and have one particular characteristic. So that's our sample proportion. So let's take a look at this idea of point estimate. So a point estimate is really just a different name for a sample statistic. Our interactive assignment defined a point estimate as the value of a statistic that estimates the value of a parameter. So it's just a statistic. We're just using it now with this idea of estimating. So we did have an example, and this actually came from the interactive assignment. In a trial of 200 patients who receive 10 milligram doses of a drug daily, 36 reported a headache as a side effect. Obtain a point estimate. So a point estimate is going to be a single value that estimates a parameter for the population proportion of patients who received 10 milligram doses of a drug daily and reported a headache as a side effect. So we're going to find p hat, our sample proportion. And we find that just by doing x over n. This is just like if I asked you, what proportion of these patients had a headache? If I'd left off sample and I left off this idea of point estimate and I just asked you that question, I'm pretty sure most all of you could tell me how to find that value. And that would be to take 36 people who reported that they had a headache out of all 200, and that would give us our proportion. And sure enough, that's exactly what we do. And in this case, it should give us 0.18 as our proportion, or 18% if we were asked for a percentage. So we've talked about a point estimate. Now, what about an interval estimate, or a confidence interval that we're going to learn about in this chapter? A confidence interval, or an interval estimate, is a better way of giving an estimate for based on a sample, because of the one thing that hopefully we all remember, the one thing about samples that I want you to be able to repeat even 10 years from now, is that samples vary. We've said that over and over again. We've taken samples, we've done things to get data, and we've noticed that samples vary. That is just a universal truth that we can always rely on. And because of that, our point estimate, which remember is just our sample value, our sample statistic, is not always the best estimate, because somebody else could come along and find a new sample statistic, and it's going to be different more likely than not. And that's okay, because we know samples vary. However, if we could give, instead of a point estimate, if we could give an interval estimate, and just to be very, very clear, when we say interval, all we're talking about is just a range of values. So if I have an interval estimate, I have a range of values that I'm using to estimate. I'm going to say that I think that my population proportion is somewhere between these two numbers, rather than saying I believe that my population proportion is this one number. So that, see how that gives us a little more authority. And this idea of confidence comes in when we want to be able to say, how sure are we that our interval will hold that value? Well, I could just make up numbers and say, I'm about 50% confident that I don't even know what to try and guess on, but I could, I'm a little more confident than 50% if it came to left-handedness, because I know that's around 10%. So I could say that I'm 75% confident, if I'm just guessing, that of all of our students in all three classes, that maybe somewhere between 8 and 12% of my students are left-handed. That's not very confident though. 75 may sound like a lot, but that means I'm got a 25% chance of being wrong. I don't want to just guess. I want to use statistical principles that we've covered so far and this idea of probability that we've talked about to make sure that I can be more confident. So how can I be very confident about that range of values? Well, I can do some things on the calculator, and I can let statistics guide my range of values. All right, so you may have seen this picture in the interactive assignment, and hopefully you worked through it or read through the part that was there. But I will say that this wasn't the clearest description, the text on this page of the interactive assignment. So I just wanted to point out, this is really just the same idea that we had when we talked about the empirical rule. So remember, with the empirical rule, we had anytime we have a normal curve, let me say that within 1 standard deviation of the mean, we have 68% of our data. Within 2 standard deviations of our mean, we have 95% of the data. And then within 3 standard deviations of the mean, I'm not going to write it, but we had 99.7%. So this right here, this 2 standard deviations away, we wrote down as mu minus 2 standard deviations, and then mu plus 2 standard deviations. Now, the notation here, this sigma sub p hat, that's the standard error based on finding the square root of p times 1 minus p over n, I think, if that's maybe something like that. Anyway, the point is, we don't need to worry about this value, but we do need to understand that that is a standard deviation or a standard error, and that's the same thing that we're going to be using. The idea of it is that we are 1.96. That's really close to this too. This is just a more precise value. This is the same thing as having the middle 95%. Just like this. So this is the same idea that we're seeing in both cases. This middle 95% is within 2 standard deviations of the mean. The difference with the 1.96 is just that we're using the exact value rather than the estimated value of 1 standard deviation, 2 standard deviations, 3 standard deviations. So please don't let that confuse you. I think this 1.96 is actually one of the answers. So if it's to one of the questions about how many standard errors, you're more than a certain number of standard errors away from the mean, that's basically saying that you are more than, or you're outside of this area. That's what that's referring to on that question. So the empirical rule is still kind of holding here. We're just getting more precise values. All right, so one of the biggest questions I usually get from students when we're working on confidence intervals is, what is confidence? What is this percentage that we're using? Because it often gets confused with probability, because we've just talked about a lot of probability questions we've done in chapter 6, 7, and 8. We've talked about, what's the probability that such and such happens? And we found, there's a 28% chance or whatever. And so we've been using percentages for probability for a lot of the class, and now we're using it for something different. And I have a great picture that I think can help show, and if you did the simulation in the interactive assignment, then you've seen this on a larger scale. I did this kind of smaller just so we can really see what's happening with it. And I'll zoom this down in just a second, but for now, I'm going to make it to where we can see the whole thing. So we've got this idea of coverage of a confidence interval. So I've created 20 95% confidence intervals from a population that samples that came from a population where the population parameter was 40% or 0.4. I took samples of size 100 and I did 20 simulations. Now in the example that you do in the interactive assignment, it's really great because you actually get to see like 1,000 simulations. And what does that look like? But in this one, just for a quick overview, I've done 20 simulations. And I've had 19 intervals, all these that are green, 19 intervals that cover the population parameter, the population proportion, and 5% do not. 1 out of 20, which is 5%, as you can see here, did not include that population proportion. In fact, it's quite a ways off. Now, what that really means, or what that looks like as far as our class, I've had people who want to try and say, trying to make this straight, I'm not doing too good of a job. I think it's just going to stay kind of crooked. I've had people try to say, and I'll put this in red because this is not right. So I'll even write, this is the wrong interpretation. 95% of the time, our interval will include the parameter. Or that there's a 95% chance that the parameter is in the interval. And neither of those are correct interpretation. Our correct interpretation is that if we were to do several, hundreds, thousands, however many, lots and lots of confidence intervals, if we were to take lots of samples, find the sample statistic to use as a point estimate, and then create a confidence interval around that point estimate, then 95% of those intervals will cover and include the proportion. So it's not this idea of there's a 95% chance that the parameter is in the interval. All right, and then just to reiterate one more time, 95% confident. I mean, of course, it could be 99 or 90, but specifically just, thinking about this, 95% confident. The 95% in a 95% confidence interval represents the proportion of all samples that will result in intervals that include the population proportion. This is simply just looking at the same idea as the normal CDF, the normal curve. 95% of the time will be within 2 standard deviations, and so we know that wherever our middle of our interval is, which will be our point estimate will be in the middle. That middle point will be within that 95%, and then 5% of the time will be outside of that. So when we go out and make a 95% confidence interval, we find the margin of error and stretch it out to an interval, we're not going to get close enough to that parameter. And so here's a clearer idea of what that 95% confidence means. So, and this comes straight from our textbook. The 95% in a 95% confidence interval represents the proportion of all samples that will result in intervals that include the population proportion. So I might have a simulation of 1,000 intervals, and only a few of them don't hit the interval or don't hit the parameter. The first time I pulled up the simulation applet in the interactive assignment, I had 98 out of 100 intervals that included the parameter, and only 2 that did not cover it. And so even though I was making 95% confidence intervals, that set of simulations, those 100 samples, it was 98 of them. So it wasn't 95%, it was 98%. So it's all samples. That's the key difference there. It's, 95% of all samples, when we create a confidence interval from those, will result in intervals that include the population proportion, or the population mean, or the population standard deviation. Basically the population parameter. I think this one, when I copied it, was specifically for proportions because we're in section 9.1.